Hello, today I'll present DiffSim, a new approach to evaluating visual similarity using pre-trained diffusion models. In a nutshell, instead of compressing images into single vectors or relying on costly user studies, we tap into the UNet attention maps inside Stable Diffusion to produce a similarity score that aligns well with human judgment. I'll show the idea, the metric called aligned attention score, benchmarks we created, and experiments that demonstrate strong gains especially for style and appearance consistency. Why do we need a new similarity metric? Popular metrics like CLIP, Dino, and OPIPS are useful but often miss subtle appearance and style differences. Human studies can be expensive and inconsistent. Our key observation is that pre-trained diffusion models, specifically the denoising UNet, contain attention maps that already encode spatial alignment and appearance details. If we can leverage those attentions correctly, we can measure similarity that better reflects appearance and fine-grained style without extra fine-tuning. Concretely, our contributions are threefold. First, we propose DiffSim, a plug-and-play similarity metric using pre-trained diffusion UNets. Second, we introduce aligned attention score, a simple but effective attention-based alignment and similarity computation for dense latent maps. Third, we present two new benchmarks, SREF for style similarity and IP bench for instance or character consistency, and show that DiffSim performs strongly on these and existing datasets. Here is the architecture overview of our method. DiffSim leverages the implicit alignment mechanism of attention to align two images at the style or semantic level, followed by similarity computation. For two images A and B, we take the attended outputs when queries, keys and values come from A, and compare that to the attended outputs when the same queries come from A but keys and values are from B. We compute cosine similarity between those attended outputs. We do the same with queries from B, then symmetrize. This AAS aligns dense feature maps implicitly, avoids naive pixel-wise matching, and preserves spatial detail. We implement three practical flavors for DiffSim. DiffSim computes AAS in UNet self-attention layers and is our default. It's especially strong on style and appearance. DiffSim uses IP Adapter Plus to turn image patches into IP tokens and computes cross-attention AAS useful for instance-level comparisons. Finally, the same AAS idea generalizes. We build CLIP AAS and Dino AAS by applying AAS to transformer self-attention layers in those encoders. To test the metric, we built two new benchmarks. SREF contains 508 human-curated styles, each represented by 4 reference images created with Midjourney SREF. IP bench contains 299 IP characters and graded variants for instance consistency. We also evaluate on established datasets, Nights, DreamBench++, Qt, TID 2013, Instance Style, and a TikTok video dataset for temporal appearance consistency. Here's our main results. Across benchmarks, DiffSim is consistently strong. On Nights we are the best. On style benchmarks like SREF and Instance Style we substantially outperform baselines. On IP we lead as well. CLIP and Dino remain competitive on some semantic tasks, but DiffSim shines on appearance and style, which is where attention alignment helps the most. We also show an ensemble of CLIP, Dino and DiffSim improves performance further. We ran several ablations to verify design choices. Most importantly, replacing AAS with a direct cosine on diffusion features greatly reduces performance. Attention alignment is the key. CLIP AAS and Dino AAS improve over their raw features on some tasks, showing AAS generalizes. We also compared DiffSim on SD 1.5 versus SDXL. Larger models may produce more diffuse attentions, sometimes hurting performance. Here are qualitative retrieval examples. On SREF style benchmark, DiffSim retrieves images that truly match appearance and texture cues, whereas CLIP often prioritizes category. On Coco, DiffSim retrieves images that match not only semantics but background and composition. On IP, our nearest neighbors maintain character consistency. These visuals illustrate how AAS captures fine appearance details that typical global descriptors miss. We also analyzed how choices affect performance. First, denoising time step matters. High T favors style and low-level features. Low T favors semantic or instance matching. Block selection matters too. Shallow blocks give style signals, middle blocks help instance matching. Resolution has small effects, generally 512 is fine, with modest gains for higher resolution on high-res benchmarks. Use these knobs depending on whether you prioritize style or semantics. There are still some limitations for DiffSim. First, DiffSim can overemphasize background when the main subject is small, leading to mismatches. Cropping or using a foreground detector helps. Besides, very large models with entangled attentions can weaken signal. Also, some extreme out-of-domain cases still trip the metric. These are actionable. Combine DiffSim with foreground priors, or ensemble with other metrics to mitigate failure modes. To wrap up, DiffSim is a simple, plug-and-play metric that leverages pre-trained diffusion unit attention to compute robust visual similarity. AAS provides implicit alignment for dense latent maps and delivers particularly strong performance on style and appearance benchmarks without fine-tuning. Future directions include better foreground weighting, video metric extensions, and adapting AAS to new diffusion backbones. That's all for my presentation. Thank you very much for listening.